All right, the recording is up. The video from Monday will be posted tomorrow, I think, along with the video from today. We're gonna continue on from lecture 2, which let us review the content of lecture 2 quickly because it's a kind of like the first intro to architecture. So we talk about how do we actually talk to the computer, right? Computer can only read ones and zero in binary. Right? The reason behind that is because, well, you just send electrical signals, high voltage, low voltage, and that's simple to actually build the hardware. And binary format is good enough to represent things like a string, character, basically anything you can think of, right? So the idea of actually talking to the computer is to basically to come up with a way to represent our human language or human instruction in binary format, where the commands are in binary and data are in binary. And with that, if we declare that, hey, that's a language, computer can tell, okay, this particular binary corresponds to an add, this one corresponds to a multiply. So you can actually run a program. Right? And you can use this as an interface between assembly code and a computer. And we talk about the ISA versus microarchitecture, right? ISA defines the list of commands in assembly language that the microarchitecture can understand. An example ISA are things like 10, things like x86, ARM, right? These are the ISA. The microarchitecture is the hardware inside the CPU, how they implement, right? How they implement the chip to support the ISA and get the most out of the chip area in terms of performance or power saving. And the microprocessor that you buy, basically things that you buy, the Intel i7, i9, i5, these are essentially ISA plus microarchitecture. It provides the programmer an interface between the software down to the circuit so you can have a functioning computer. And here are some of the key elements of the ISA, things like memory organization, right, where you have address space, number of unique locations, whether it's addressable in each individual bytes, each individual bits, 64 bits or 32 bits. And here's the exercise I gave you last class on Monday. Hopefully you think about it, at least think about this a little bit. We have to also look at virtual memory support, also issue like big versus little Indian. Inside the ISA, they also specified register, a really, really fast temporary memory. We're going to talk a little bit about what is a register today for the context of your assignment. Basically, we're going to talk a little bit more in detail. What do I do for your assignments to model register? And what's the benefit is basically this is fast temporary storage that provide data locality. Right, so that's a review of the last lecture. If you have any questions, feel free to ask on the chat right now or in Discord. We're gonna move on to the single cycle architecture. Feel free to type in question any point in time. I'm gonna look at the chat and I'm gonna answer your questions. All right. So let's move on to today's topic. Single cycle architecture. Let's actually build the chip. This is going to be a simple chip. Right? That would run a real program, but it's going to be simple, it's going to be slow. The first thing we need to talk about is what's visible to programmer versus what is not visible. Things that are visible to programmer, we call this architectural state. Things like the name of the register, right? In a typical fashion, you can have register 0, register 1. In x86, it can be those like things like EAX, EBX, right? You've seen this before, ECX. These are register. There's also a program counter or the instruction pointer, and we'll go into more detail on what is the purpose of the program counter. But basically, it points to the current, right? The current line of the assembly, right? Assembly code that you are running, it gives you a location of this is the line in code that you're running. There's also memory. Right? The memory is visible to the programmer. Why? You used pointer before, right? How many of you used pointer before? Hopefully every one of you. Are you still with me? Hello? So the way that you use pointer is it's an interface that you can control the memory from the program, and the programmer can directly see and handle this value. Right? You can modify the register on assembly code. You can modify how you manage the memory. You can change the address. You can access different address. You can get the data. That's also the part that you cannot see. The parts you cannot see. The difference here is we call this microarchitectural state. The difference here is the word micro, right? There's no way for the programmer to access this. We don't trust you from the hardware point of view. Basically, we will perform this optimization such that programmer doesn't have to worry about this. And what we tell the software programmer is basically, trust us, your program will be faster with this modification, with this optimization. And here are some of the example, right? The value of the certain cache block, you can't modify them manually. You cannot look at the intermediate value of register in the middle of the 5-stage pipeline. So these are still unfamiliar terminology. We'll go through what does it mean to be pipeline. What is a pipeline design? That would come up in the next 2 lectures. For now, just be aware that there are so many things inside the hardware that we don't tell you because so that basically we don't want you to worry about too much about what those things are. But it makes your program faster. These days, there are actually a lot of design to expose some of these micro-architectural states to the software so that you can control some of this to make it such that your program is actually even faster. We'll kind of discuss about it toward the end of the class, not this class, but the semester. And now that we have the ISA that we developed from the lecture 2, right? Let's assume right now it's a MIPS ISA. We basically have a method to command our computer, right? How about the hardware? Basically, you have to connect all the circuits together, right? And how do you actually make sure the machine that you build can understand the method that you want to do? Basically, these are the key. You have architectural state, right? What programmer see? Let's say you are at state 1. When you process one instruction in assembly code, what actually happens is you move from state 1 to state 2. You change the hardware state from state 1 to state 2. When you finish your program, hopefully the state channel, sorry, fat finger again. When you finish running your program, hopefully the architectural state represent what the program is supposed to do, right? And what do we expect from this? Basically, the ISA that we have, right, specify what the second state looked like given the instruction and given the earlier state, right? Given the earlier state. What's missing here is in many hardware design that actually can be immediate state that are implemented in a microarchitecture level, things that we don't tell you that is going on from state 1 to state 2. And there can be any number of these immediate steps in the middle. This is done by design. The goal, more than half, the goal is to get the most out of the transistor that you have to get more performance, right? You can move from architecture state 1 to state 2 in one clock cycle. That's one design. You can have 3 intermediate steps from state 1 to temp 1, temp 2, temp 3. into architectural state 2, where you run across multiple cycles. And we'll learn in this class, we'll learn what are the trade-offs. For this lecture, we're gonna focus on this particular design. In one cycle, you move from architecture step 1 to step 2. And here are some background that I want you to understand. How many of you heard about the word wires? What does wires mean? What does wires mean? It's just, yes, it's just a physical wires. It conducts electricity, right? So let's say you have component 1. It connects to component 2. These are wires. Let's say I put in data over here. Component 2 would see the same data, right? It's just physical wires that transfer electron. So if I send out data through the wires, the other side would get my data. It's as simple as that. Any questions about the wires? Hopefully not. But think about it this way. Whenever we draw lines in any design for this class, for the purpose of this class, they are wires. If you send out some output, the other receiving side should get the input. Should be the same input. All right. So hopefully that's clear. Register are things that store data. Basically, you have data come in, right? And this data will be stored inside the register, right? So this thing is a register. And it produces the output, input, right? And these data can get overwritten, right? So in the next clock cycle, it might get overwritten into a new data. You can overwrite the register. If you don't overwrite it, it's going to maintain the old data. Any question about how register work? Basically, you have two choices: maintain the old data or overwrite it. The third thing called MUPS. It takes n input, so n input. Usually we draw it using this kind of rectangle. I actually forgot what's the name of this rectangle. There'll be a select line. The select line, depending on what you're selecting, it would pick one of these wires and connect them. Basically, you have multiple inputs. Select line would tell which input goes to the output. That's called a mux. A demux is the inverse of this. You have one input, and then the select line would select which wires here gets the output. Any questions about these 4 components? This is almost like similar to if else, right? And this is just basically direct where the output should go. And I promise you, for your assignment, you're not going to deal a lot with this, but somehow I will draw them on the design. So I hope that at least when you see lines, those are wires. When you see some boxes, I'm going to tell you what are those boxes. Have you seen this in a digital design class? Okay, cool. All right, awesome. So some more background, the combinational logic, think of it this way. It implements the logic you want to do: add, multiply, divide, and or anything that is your instruction. Sequential logic are logic that you control using a clock. A clock is a signal that changes the voltage, right? So low voltage and high voltage. And the clock would be something like this. It keeps changing the voltage. Anyone want to guess what's the purpose of having a clock? What is the purpose of having a clock? Move data, yes. Reading input, yes. Synchronize instruction, yes. Basically, it's used to advance time, right? You remember you have, let's say you have 3 instructions, right? Instruction 1, instruction 2, and instruction 3, right? Basically, you're gonna run instruction 1, process it, then process instruction 2, then process instruction 3. These are done synchronously using the clock. The clock would ensure that 1 has to happen before 2 and 2 has to happen before 3. It tells the time. That's why we name it clock. The last thing I want to tell you is something called critical path. Critical path. The longest path in your design, right? that that take basically that takes the most amount of time to send the data over from source to destination, right? Basically, these determine how long your design is. How long does it take for me to move the electron from one side to another? From one side to another. So what would happen if I have a design that that has a really long critical path? My design is going to be slow, right? Because I cannot clock it that quickly. If I clock it too quickly, what happens if my electron haven't moved to the destination yet and you clock it? The electron is like, okay, I haven't reached the destination. Your logic would get buggy. You need to wait. You need to wait at least that much amount of time. So critical path tells you your clock, right? In your Intel processor that you buy these days, when you look at say 3.7 gigahertz, it means that your critical path is at least that fast. At least that fast. You can safely clock it at 3.7 gigahertz and everything will be fine. How many of you overclocked your CPU before? Or overclock your machine to make the clock faster? Yes, no. Has anyone tried that before? Okay, lack of answer, I assume no. But basically, if you overclock your machine, one thing that can happen is it won't boot. If you make it too fast, because sometimes that this thing happen, if you overclock thing, basically you make the clock faster. The critical path is too long, so you can't really have a functional CPU or functional memory when you clock it that fast. Another thing that can happen when you overclock things is you heat things up, right? The temperature increases. That's why when you want to overclock your machine, you need a really good cooler to cool down your logic. When you cool these components down, the critical path will shrink a little bit. This is like physics, basically. It allows you to maintain higher clock speed without crashing your system. All right. So today we will assume we are going to build a processor where the source to the destination is in one cycle. It's going to be a super long critical path. It's going to be a super long critical path, but it will work. It will take one single cycle to process one instruction. And that's assumption. Let's assume that architecture state 1 go to some combinational logic, and you get architecture state 2. Sequential logic would determine, hey, move the clock. So you go to the next clock cycle from AS2, then you move to AS3. What determines the critical path of our combinational logic is basically the longest path that you see when you draw it out. The slowest instruction. So let me ask you this. Anyone want to take a guess how long do I need to add two numbers together? Let's just do an add. How many nanoseconds that would take? Within 10, right? Within 10, depending on how you design your chip, right? Within like 1 to 10 nanoseconds for sure. Or sometimes if you throw in so many transistors, it can even be faster than that. How about getting one piece of data from the main memory? So there's a compute instruction. It can range from like 12 to 50 to 100, depending on how much bandwidth consumption your program is. Sometimes you queue things up over there. How about going to the disk? Way more than that in millisecond. Yep, in microsecond or millisecond, depending on the size of the load that you want to get from the I/O, right? Yes. So this means that my slowest instruction determine the clock, right? Now you see why this design is going to be super slow, right? It's going to be in the range of kilohertz rather than gigahertz. Kilohertz, yeah. That's like 1950, 1970, right? How many of you have seen a computer back in like Pentium day where you have a turbo button and it has like 200 megahertz for the clock? Back in the day, even those machines doesn't use a single cycle processor design. It's actually way more complicated than this. Today we're gonna build, or at least I'll give you the high level overview on how to build this simple processor that is in kilohertz. And we'll move on from that point. We'll make things faster. Trust me, your assignment eventually will become better. It will become better, and your processor will become faster. But in a single cycle processor, the slowest instruction determine the clock cycle. So what if instruction need to access memory or the I/O? Then you are basically screwed. You are going to have a 1 kilohertz processor. So to simplify things, but let's still study how you can implement a basic processor. Right? So hopefully you're excited about, hey, we can think about building chips, right? We can think about building chips. And in the assignments, I'm actually asking you to simulate a real chip. So the first thing that I want you to know is, because actually this is one of the answer in your poll as well, you cares about performance optimization. So the first question I want to ask you is, how do I want to measure performance, right? How do I actually want to measure performance? Instruction are processed in steps. Right? Instruction are processed in steps. So we call from earlier lectures, instruction are in the memory. So the steps are this. Generally, this is what happens. You go get the instruction, right, from the memory. You decode the instruction, figure out what the instruction do. evaluate the address. If you need to get something from main memory again, let's say it's a load or store instruction or move instruction that involve memory accesses, you check what's my address. Right? If you want to assign something to an array, what's the address? Fetch the overrun, right? Get source 1 and source 2, right? For your instruction, if I want to add the two number, what's my operand? What's the left side and right side of my add? So that you can add the two number together. Execute, run it, and then write the result back. Right? Or somehow we call commit, right? Give result. These are simple steps, right? Basically, I go check my instruction. Once I have the instruction, I look at the binary and figure out what does the instruction do. Based on that, you're gonna actually get all the data required for the instruction and run. And once you run it, you get the output, you store the output. And not all instruction requires all the steps, right? Not all instruction require the steps. So the way to measure performance, right? One of the common way to measure the performance of a processor, sometimes we call it CPI or cycle per instruction, right? Anyone want to take a guess what is cycle per instruction? What is the definition of this? You want guess? All right. Basically, how many clock cycle does it take to finish the instruction on average? Right. So I can use that to tell the performance of my processor. Right. Let's say the CPI is 10. Within on average each instruction take 10 cycles. You can reverse this as well. These days, all your CPU, even a GPU, they measure in instruction per cycle, right? Because our processor these days are good enough that you can process more than one instruction, basically more than one instruction per cycle. And we call this IPC. Basically, it's a reverse of that, of the CPI. And let's talk about single cycle versus multi-cycle, which we'll talk about in lecture 4. Basically, in single cycle processor, every step is done in one clock cycle. In multi-cycle processor, we'll add more cycles to finish your instruction. There'll be a lot of trade-off here, but each step can now take as many cycles to complete. But if you're doing an add, it's gonna finish faster than a multiply. Okay? It's gonna finish faster than a multiply, and we'll go through an example of why do you get a benefit, basically? Why do you actually get a benefit in a real computer? And our modern computer are built this way. All right. So the next thing I want to talk about before we start drawing some chip design is what is the data path and what's the control logic? So these are two terminology that I want to make sure you understand. You might refer to this sometime when I'm drawing things. Think of it this way. When you process the instruction, right, when you are processing an instruction, you transform data D1 into D1 prime. That's it. You change the data from one value into another. Right? Think of it as a math function. Everything can trace back to a math function. And this is done through what we call a functional unit, or the ALU, arithmetic and logic units. Can be also load store unit, right, that handle load and handle store. It basically performs the operation on the data. Right? An instruction tells what the operation is. So to process the instruction consists of two components. Data path is the hardware. Basically, anything that are hardware that deal with changing D1, data D1 to D1 prime, basically change the data from one value to another. That's the data path. Things like the logic that implement the add, the multiply, those are data path. The actual structure that move data around, like wires, mux, All those things are a part of the data path. Register that store value is also a part of the data path. So now you might ask, so what is the control logic? Right? Control logic is, as the name suggests, is a signal that go into each component, each data path to tell do this, do that, do that, do that. Disable this part, enable this part, disable this part in this cycle, enable this part at that cycle to make sure you can run the correct instruction in the correct way so you get the correct program running. Right? So I look at your question. So you ask, is this a program? I'm confused. What do you mean by is this a program? I'm sorry. Oh, control logic. No, it's actually like a hardware control signal, right? So it's not it's built in internally inside your program. It allows basically you're not your program doesn't tell what are the control logic. It does, but given the instruction, there will be a hardware inside your processor to tell do this, do that, this part, this component, do this component, do that, read the register from R0, read the register from R5, add them together, write the register to R1. Move the data from here to here, move the data from here to here, select this, select that. Those are the control logic. Is somehow we call it control signal. Basically, you signal each component to tell what it's supposed to do. Hardware consists of two things: data path and control logic. The actual things that are used to transform D1 to D1 prime, and the control signals to control all the hardware. So hopefully that answers your question. Does it answer your question? Okay, cool. And with multi-cycle, all the control in a single cycle processor, right? Every single control signal are generated in the same cycle. Every single part, because we do everything in one cycle, right? You generate all the control signal all together for all the data paths. So in one cycle, you're gonna get D1 transformed to D1 prime. Multi-cycle processor, the control signal that are needed for the next cycle is generated in the current cycle. This allows you to decouple the latency of the control signal to the data path. We'll talk about this in detail with an example in the next lecture. Basically, right now, let's go back to the focus of your assignment, right? And how you can build assignment one, which is a MIPS R4000 architecture using single cycle. So assignment one is a single cycle implementation of your MIPS R4000. The components that you have, right? We'll go to one at a time. It obviously need to have the program counter. You feed in the program counter tells it stores the value that correspond to the address of the current instruction, right? The address of the current instruction. And this program counter get incremented after you finish the current instruction. After you finish the current instruction, you increment program counter by 4. Why by 4? Because it's a 32-bit machine. Each instruction is 4 bytes. So the next address for the instruction is PC plus 4. Right? This is PC program counter. The next instruction would be located at PC plus 4. And inside the memory, there's a different region for the data itself, right? This is static data. Something like an array that you declare. This is where your program is stored. And this is where dynamic data is stored. Because you can grow and shrink the stack. Your task in the assignment is, I give you a skeleton code that lays out a lot of the hardware component, i.e. the data path, right? You finish the function called process instruction in C. Everything is done in C language. I'm not asking you to do this in the hardware description language because I don't want you to learn a new language, basically. Use C. It's a lot more convenient. Basically, it means that you need to send the correct data and control signal to modify each piece of the simulator that I wrote for you. Things like, what's the next value of the PC when I proceed to the next instruction? Given a bit pattern, what is the operation? Is it an add, branch, multiply, right? Which register you're selecting for source 1, source 2? Is this from R0? Is this from R5? Is the destination at R6? Right? You figure it out from the binary. And what address you're loading, right? Are you loading from address 0xA0? What's the value there? Once it's done, is it loading to a certain register? Right? Is it to R5? Basically, what you would do is you say R5 equals this value for the cycle because you finished loading, right? And do you need to update any status specs? All right. So a bit monologuing for a while. I'm gonna start drawing a simple processor that we just described, right? So this is going to go through some more information. Before we move on to the actual design phase, let's take a quick 8 minutes break. You meet at 12:50. Is that okay? Okay, so let's do a 8 minutes break. We'll be back at 12:50. If you have any questions, type in on the chat. Meet you all in now 7 minutes. All right, take a break, get coffee, and we'll see everyone in a bit. right, are you guys back? Or not? There's no way for me to check if you're back or not, actually. Okay, it's 12:50. I assume everyone is back, right? So let's assume so. Let's continue on to drawing a simple processor. The reason why I said drawing is in hardware design, one of the first steps always often enough is to actually draw it out on a whiteboard, on a piece of paper. Draw your design out by looking at the task that you have to do, right? When you want to process an instruction, what's the first thing that you should do? Anyone want to take a guess? What's the first thing that you need to do? You read the instruction, right? You go and get the instruction. So the first step is basically we call it fetch the instruction. And where's my instruction? When you run a program, where is the instruction? Where's that program? Where's my program located? When I run a program, it get copied to the main memory, right? Everything is in main memory in DRAM, correct? Basically, your instruction would be somewhere in the memory. Then let's assume it's right here. What do we use for the address of the current instruction? What do we use as a current address of our instruction that we're running right now? We covered this about 20 minutes ago. Someone has to answer this. You can go back on the slide to, well, I don't think I posted this slide yet, actually. Remember the program counter? What is a program counter? What does it store inside the program counter? All right, try not to sleep through my class, please. It's pretty almost obvious that you don't listen to this part. But the program counter stored the address of the current instruction, right? The address. Can someone pick me at random address? Just put one address here that are divisible by 4. Any address that are divisible by 4. 8. Okay, let's say the value is 8, right? What it does is it would go look at the address that correspond to the value 8, and let's say it's right here. Let's say it's this line X. I would go get that data, right? Whatever that data is, basically this thing would come out, comes a piece of data that correspond to that instruction. Right? The instruction has a binary value, so it would go and look at that address and gets the data. That's where your instruction is located, and that's the data corresponding to that particular instruction. All right, so when I move to the next cycle, assuming that this is not a control flow, right? Assuming this is a normal compute operation, what is the new value of my program counter? Starting from address 8, where is my next instruction? What's the address? 12. Yeah. So you move on to address 12. You go here, right? Which is the next, literally the next line here, right? Line x plus 1. You look at the data comes out, and you get the next instruction, right? This is how you fetch the instruction. You go to the address corresponding to the program counter. Inside the memory, it will contain your program. It's as simple as that. In our assignment, we'll tell you what's the initial program counter value, and that's where the program, the first line of your program will be located. You go to that line, you process that instruction, then you move to the next line. You process the next instruction, you move to the next line. Any questions about the fetching part? We call this fetch the instruction. Any question about this? So what do we do after we fetch? What's the second step? How long does it take to fetch? So decode is the second step. Yes, that's correct. So let me answer the first question. How long does it take to do this? This depends on how long does it take to access, right? The memory, which seems long. There are a lot of techniques that we apply on your CPU to make it such that it's basically one cycle. So in this case, without optimization, it's going to take as long as the time you need to access the main memory. But with caching, we use caching for instruction as well. We call it iCache. It would behave as if it's one cycle. Most of the time. Most of the time, it's going to be close to one cycle or one cycle. So the second step, as Cham said, is decode the instruction. Which is basically now that you have the data, right? The data that correspond to the instruction, which is basically a bunch of ones and zero, right? From here, you look at the pattern, then you check back with the ISA. The ISA defines if you see this pattern, this is what they mean. If you see this pattern, this is what they mean. If you see this pattern, this is what they mean. So let's give one example. Let's say you see a pattern, and basically this corresponds to add. You want to add two numbers together by doing this. R6 equal R5 plus R4. It will be a specific pattern that if you look at the bits, it would exactly correspond to you are going to add R5 with R4, write the result to R6. That's what the code is doing. Then 2.1, the code would generate all the control signal so that the hardware actually perform at R6 equal R5 plus R4. Any question from this? Basically, decoder, that will be a unit called a decoder. So basically you have fetch, right? You fetch the instruction. The instruction gets fed to the decoder. Decoder send out. Okay, let me actually use a different color. It would send out the control signal, right, to all the components. So these are control signal to correctly perform the exactly what the instruction tells you to do. Any questions about this? You look at the bit pattern. The decoder say, okay, this component do this component do that. It's kind of like if you look at say the orchestra, right? This would be the conductor. Tell every single piece inside the band to do this by generating the control signal. It sends the signal to all the pieces. This piece to this piece to this piece to this. Any questions about the decoder? Because this is the big part of your assignment one. What are the control signal that you're sending? How do we pick R5? In this case, like pick R4 and then add them together and write it to R6. So assume that you got this part. The next thing, what do you do? So next thing, I'm gonna combine multiple steps together. Basically, the third part is you actually execute the instruction, right? Execute the instruction. And I cannot write for some reason. I want to write in the word instruction. So depending on the control signal that comes in, right? One thing, multiple things would happen. For example, you have this little area called register file, which is where all the registers located. What were we adding? We are adding R4 and R5, right? So the control signal would come in and say, hey, R4 and R5, I'm gonna take these two values, take it R4 and R5, 5. Take it so that you got both R4 and R5. Then the control signal would go to the ALU, right, the arithmetic and logic unit, and say, hey, the adder control signal would take R4, feed it to the adder, right, R5, so that it produce the result. Basically, you actually perform the instruction. You actually perform the instruction. If you want to load the data, then the control signal send the address. They send the address so you can load the instruction to get the data. Right? So once you have the results, what do you do? What is the last step? Basically, what's the last step after you got the result of your instruction? You write the result, right? So let's say you have add. So this is basically R6 equal R5 plus R4. And you already got this. So these are the results, right? What you want to do in this steps is you have again the register files, right? You have R4, R5 right here. And let's say this is where R6 is. The control signal would come in and say, hey, I got the results right here. Plus update PC value, right, to PC plus 4. Any questions about this? This is basically the 4 main steps that you have to do to run an instruction inside your simulator. And in the real hardware, it's the same process, basically. You look at the instruction pattern, you send the correct control signal to all the hardware parts, and you run it. Any questions so far? All right, so I'm gonna put everything together from the 4 steps that we talk about. What does fetch do? And let me make an assumption this is where the memory is. What does fetch do? You have the PC program counter. What do I do here? Go to the memory. Yes, you go to the memory, get the instruction. So what do I do next? So this is the address. Forward the data. Right? Forward the data to the decoder. This is the data. DATA. The data goes into the decoder. Yep, it interprets what you do based on the data that we fetch. Inside here, let's say this is where the register files is, but where the value of R0, R1, R2, R3, R4, R5 is. Decoder would send a control signal, and let me make sure I'm consistent with the color. So this is the control signal to say, hey, get this from the register files. It would then also have a MUIC right here. It would select, right? Select the, well, MUIC is the data path. So again, let me make sure I'm consistent with the color. MUIC. The select would select, right? Would select R4 and R5, pass R4 and R5 to the adder, right? Which is the ALU. Inside the execution or memory stage, if this is not an add instruction, let's say it's a load instruction, right? This control signal can select, right? Can select the signal such that the address goes to the memory so that you can load the data, so that the data comes back as the piece of data you want to load coming from the main memory. So this is the results, right? Then again, that's going to be MUIC here, where the select from the decoder, right? Select from the decoder would go all the way. Oops, wrong color, my bad. Would go all the way from the decoder again. Decoder tell what everything is doing. Put here into the select signal, right? As an input, select that the results. Not going to pick the data because this is an add instruction, so we'll pick the results. The data comes here, right? Come out, so this is the results. Where does the data go? Where should I put this result back to if it's an add instruction? If it's an add instruction, where do I put the results back to? The result of the add. So that's the new PC. That's the next step, basically. The first thing is we got the results, right? We want to say, hey, R6 is going to equal to this results, right? R6 is register. R6 is from register. So basically you forward the result, right? Let me skip this, put it in the register. Then the decoder again would send the select, right? The select signal that say, hey, this is R6. Select R6 so that you can write the result into R6. Then decoder would again tell the PC, right? Select PC plus 4. Why do we have to select PC plus 4? Sometimes you are jumping. right? If you jump, PC would move to the new value. It's not PC plus 4 anymore. So the decoder have to tell, okay, what's the value of my PC for the next cycle? All right. Any questions about this design? Next lecture, there'll be a much better drawing, but I want to draw it step by step here, so it's kind of look ugly right now. You'll see a much better design the next lecture. At least better drawing. Not a better design, but basically it's more clear. It will be drawn on PowerPoint. I already have it. I choose to delete it for this particular slide, so I can draw it one by one by one. Any questions about this? Now we have a ship. It's a semi-functional ship that can only do an add or load something from the memory. But you can imagine if you have the adder, you have multiplier, you have the like arithmetic and logic units, then it's going to be a fully functional ship. Okay. This is a really, really, really simple ship, but it works. Why does it work? Can someone tell me why does this work? Because it implements what the ISA tells the architecture to implement. It supports the instruction it needs to support. So the programmer can write the assembly code, right? If they write the assembly code based on the guideline, the program will run. The program will run because you just have a hardware to support the whole ISA. Right? So essentially we just build a chip. It's a really wacky, simple, and slow chip, but it's a chip. We will go into the detail on how we make it fast. We go into a detail on how the modern processor works. We'll go into detail on how do I deal with memory? How do I deal better with memory? How do I deal better with all the PC plus 4? Or are we jumping, right? We call this branch prediction. You can actually predict if you see if else, you can actually predict if it will go into the if or if it will go to the else. And we are doing really well in that region. Most branch predictors around, I would say, like definitely better than 97% accuracy. So we will cover all those in this class. Hopefully you're excited. But basically, this is the content of today's lecture before we move on to the in-class exercise. Before we leave today, here's the in-class exercise. We'll switch over to Discord. Basically, I want you to write two functions in MIPS. Feel free to make any assumption you want to make, saying, hey, the register value is already declared in R4 and R5, and I want to add to the R4 and R5 together, just to add IU, R4, R5, R6, something like that. So the first one should be pretty simple, right? Really simple. Should be simple. And factorial is going to be a bit less simple, but it's going to be pretty simple as well. You look on the lecture 2 handout, we have the manual on the in-class exercise on Canvas. I also put in the link for the manual. Focus on the add instruction, multiply instruction, and branch instruction. Those are the only three you need to have a fully functional program that can add the two numbers and do factorial. Then you run it to SPIM, the simulator that we asked you to install on Monday. So hopefully you have that installed. Then you submit the screen capture that shows your results, so that it works. Let me talk a little bit about assignment 1. Assignment 1, you are going to write a simple MIPS simulator. It's simple because it's one cycle. It's a single cycle architecture. It supports most common instruction, which means that the program actually run into whatever you write here. You can write a real program and would run, right? The lab, let me properly credit the folks who make this lab. So this is done in spring 2015 in CMU for the computer architecture class. This is one of the lab. We have 7 of those. I'm actually removing a lot of those. You instead of 7, you do 3. This is a lab which I was a TA for the class. We actually make sure you can get everything and know how to build a simulator. In the CMU lab, you actually build the real ship design. So if you're curious on how you can proceed and use the actual what we call hardware description language, let me know. I have the material. If you want to try it out, I will be more than happy. I will be excited, to be honest, if you say that to me. It would take more time, so I don't recommend to do it in this semester as a part of the class because you're also taking many other classes. Otherwise, it's going to take too much of your time. But your code can run a real program. That's what I want to stress out. You can run a program on the things you're building. So hopefully you're proud of it after you've done the 3 assignments. You can put it in resume that you built a simulator for a real ship. I'm serious about that, right? It's not easy, but you learn a lot. Please keep in mind that you're going to use this code for assignment too. So please make sure it works. Because if it doesn't work, your assignment two code is going to like the first thing you have to do is to fix it. So assignment one works. Make sure it's neatly written because well, it's a proper how to program. Basically, you need to extend your code if it's not neatly written. The 3 weeks after, you're like, okay, what did I write here? I forgot. Basically, what we want you to do for assignment two is pipeline this. Okay. So there'll be the pipeline part, which is the main part, and there's the extra credit part, which you do pipeline plus some more fancy things. And thank you so much for submitting the comments. Right? Obviously, I read. I went through this last night, so I got at least the last night version of the submission. Once you are done with this class, based on your comments, I'm gonna teach you so that first you should be able to see how all the parts in hardware from the program, basically from the point of you finish writing your program, I'll tell you from that point on how everything fit together so you can see the big picture of like, okay, this is the program and this is what happened. This is something that I think is missing in a lot of architecture class. Even at CMU, when I took the class, I feel like this is something that's missing that I need to go back and think about it. It's like, then I'll have this like, aha, okay, this is how it works. So I'm gonna make sure toward the end of this class, right, toward the end of this semester, I'll make sure you have that picture in mind. I'll cover things like machine learning, deep learning, IoT optimization, how you build the hardware for machine learning, how you build the hardware for really power efficient IoT optimization that people do nowadays. There's a lot of common techniques that are being done on real chip that you can buy nowadays. How many of you use this thing called Turbo Boost in the Intel processor before? This is called Turbo Boost. Yes, no? Anyone heard about it? When you buy an Intel processor, it comes with this. So basically what it does is, if it detects that you're running only one program, right? Let's say you have a 4-core machine. Intel will say, okay, because you're not using the other 3 processor, I'm gonna boost the speed of this one processor to boost the performance of your program. And this is done in hardware. Right, so there are a lot of real techniques that you can do to actually see the performance improvement in a real chip. So I'm gonna give you more and more example as we go along in this class. So hopefully you basically appreciate things that you buy, right? that hey, it actually has a bunch of like fancy things that you can change in BIOS. Go to the BIOS and say, okay, now I know what that means, and now I know what that means. So if one thing that I would like you to try out is like if you boot things up and your machine up and check the BIOS. If you have questions about some of those, if I can answer, I'll be more than happy to answer what they mean. I'm not going to tell you that I know everything, but then I'll try my best to answer your questions. All right. I'm going to cover topics on the like when you buy parts, right? When you buy the processor, when you buy a DRAM, when you buy a main board, right? What does the specification mean so that you don't throw money away for things you do not need? Basically, you would hopefully optimize the cost, being most cost effective of when you buy a new machine. So hopefully this class, what you learn in this class help not just being a better programmer, right? But also being a better buyer. You know what you're getting in your machine. Uh, so one more thing is the comment about like some people here say, hey, are you excited about like building or knowing how to actually design a chip, right? So your assignment will kind of force you to do that. So hopefully you're excited about it. Don't feel that it's gonna be hard. I'm here to help you. It will be new. Let me put it this way. It's not hard. It's just new. The things you learn here will be new. And I can assure you in Thailand, this is probably the only class for the undergraduate degree who go this deep without, basically I'm making sure it's not too hard, but your lab will give you a lot of new things to learn. One exception is this is done in C instead of the real hardware description language. And we will expose some of the magic that we do to make your computer faster. One more thing. Next Wednesday, I have a conflict from noon to 1 o'clock. So I'm going to move the lecture time. Instead of starting at noon, I'm going to start at 1 p.m. to 2 p.m. And then the in-class exercise will be done in the evening. So you basically, I'm going to post the in-class exercise on Wednesday morning. Feel free to do it anytime you want. If you have a question, comes into the class and I'm going to answer them. If you don't want to start doing it right afterward, then I'm going to be online in Discord. So let me double check with you. What time do you prefer after 6 o'clock? What time is best for you guys? If I am going to be online in Discord for 2 hours, 7. So how about 7 to 9? Would that be okay? So I'm gonna be online between 7 p.m. to 9 p.m. Feel free to come in and if you are going to work through the in-class exercise, I'm gonna guide you through that. If you have a question about the assignment, I'm gonna guide you through that. I'm so sorry about my conflict. It's kind of pop up, so I kind of need to uh, block out noon to 1 p.m. But the class lecture will start at 1 to 2 p.m. and then there'll be a Discord session basically for the in-class exercise in the evening. All right, and that's all for the lecture today. We're back at the in-class exercise, which is right here. So I'm gonna switch over to Discord. Is that okay, or should we stay here in WebEx? Up to you. Either one is okay for me. Any preference? Are we going to Discord? Are we staying in WebEx? It's up to you. But basically, this is the time for you to do the in-class exercise. No one say anything. Can you say something? Are we switching over? Are we stick with WebEx? Otherwise, I'm gonna switch over to Discord. Okay, here's fine for me. For you. Okay. So how many people said here's fine? Okay, if either is fine for you, let's just stay here. If you have question, type it in. And you can share the screen, I believe. If you have question, you can share the screen. The only downside, everyone see your screen. So, so if you have question, type it in. You can turn on your microphone. I'll answer you either through the chat or through the microphone. All right, so let's stick in WebEx so that I don't have to boot up a new stuff on Discord. I'll stop recording right now so the video is not